Welcome to Naradar Academy. In this video, we are going to discuss about rank and nullity of a linear transformation, and we are going to solve few problems on which we are going to find rank and nullity of the given linear transformations. First, let's see the definition. Let T from V to W be a linear transformation where this V and W are vector spaces over a given field F. Okay, then dimension of T of V, that is dimension of the range of T, is called rank of T, and dimension of kernel of T is called nullity of T. That is, kernel means what? The set of all elements of V which are mapped to the zero element of W, isn't it? So dimension of the kernel of T is called nullity. Okay, let's see some important results about rank and nullity. Dimension of V can be written as rank of T plus nullity of T. Okay, then a linear transformation T from V to W is called non-singular if it is 1, 1. That is, a 1, 1 transformation is called what? Non-singular. Otherwise, if it is not 1, 1, it is called singular. Next, suppose if we have a linear transformation from V to W, then T is non-singular if and only if rank of T equal to dimension of V. So rank of T will become dimension of V means what is nullity? Nullity will become 0. So for non-singular linear transformation, what should we have? Nullity equal to 0. Okay, right. Next one, T from V to W is a linear transformation. If dimension of V is greater than dimension of W, then T is singular. Okay, singular means what? It is not 1, 1. Then final result, T from V to V is a linear transformation on a finite dimensional vector space V. Then any such non-singular linear transformation, okay, any such non-singular linear transformation will become what? Onto. That is, what should we have? T is a linear transformation from a finite dimensional vector space to itself. Okay, whatever non-singular linear transformation you have from V to V, that will obviously become an onto mapping. Okay, so with all these results, let us solve some of the problems here. So in all these following problems, we are going to find the rank and nullity of the given linear transformations. Okay, I am going to explain how to find the rank and nullity in different methods. So for each and every problem, we are going to do in a different way. Okay, so that you can use whichever you feel comfortable or whichever you will get the answer quickly, you can follow, right? The first one, T from V to W defined by T of V equal to 0 for all V belongs to capital V. So see here, this V and W, they didn't mention anything about this V and W. They are any general vector spaces, okay, defined over the field F. They didn't mention anything about this, so we don't know what are the dimension of these spaces. The only thing we know is the definition of the transformation. So what is the definition? All the vectors of V are mapped to 0. Okay. Whatever vectors are there in V, they are mapped to 0 element of W. Okay. So by means what? Kernel of T is equal to the entire V. What do you mean by kernel? The collection of elements of V which are mapped to 0 of W is called kernel. Here, since all the elements are mapped to 0, the entire V will become your kernel. Okay, so kernel of T equal to V implies dimension of kernel of T equal to dimension of V. So, but what is this? Dimension of kernel of T is our nullity. So, nullity of T equal to dimension of V. Okay, so we find what is the nullity. Next one, I have to find what is the rank of T. So, by definition, what is rank of T? Rank of T is nothing but dimension of T of V. But T of V equal to 0, no? T of V equal to 0 for every element. So, dimension of 0. But we know 0, singleton 0 is a vector space of dimension 0. So, this dimension is 0. Hence, rank of T equal to 0 and nullity equal to dimension of V. Here, I find out both the values. But it is not necessary. Because if you find any one of the values, from that itself you can write the remaining value. Because what is the relation we have? Dimension of V equal to rank plus nullity. Isn't it? So, it is enough to only find either rank or nullity. Whichever you feel easy for calculation, you can follow any one of them. If you find the rank first, then you directly write nullity equal to dimension of V. Because this is 0, no? So, directly what can you write? Nullity equal to dimension of V. Otherwise, if you find the nullity first, if you write it as nullity equal to dimension of V, then obviously what will become? The rank. Rank will become 0. Okay, right. Then, next one. Second problem. T is a linear transformation from V to V defined by T of V equal to V for all V belongs to V. Okay, this is of a similar type. As like the first problem, we don't know anything about the vector spaces. Okay, so here V is any vector space in which we defined a linear transformation as what? T of V equal to V. That is, every element is mapped to itself. So that means what? T of V, that is the range of V, range of T is equal to the entire V. Okay, therefore dimension of T of V equal to dimension of V, and hence rank of T equal to what? Dimension of V. Okay, because every element is mapped to itself. Therefore rank of T equal to dimension of V. So from this itself, what can you conclude? Nullity of T equal to 0, because here it is dimension of V, no. So rank plus nullity must be equal to dimension. So when the rank itself is equal to dimension, nullity is equal to 0. But I will show you how to find the nullity. Okay, if you want to find the nullity of T, how to find? See here, T of V equal to V, they have given, no. So only for the 0 element of this domain, T of 0 will be 0. Only for T of 0 equal to 0. That means what? Kernel of T equal to 0. So this is the 0 space. That means its dimension is also equal to 0. Therefore nullity equal to 0. So here also it's enough to find any one of the values. From that itself we can find the remaining value. Okay. Then next one. T is a linear transformation from V to V by W. What is this V by W? Quotient space. Defined by T of V equal to W plus V for all V belongs to V. Okay. Quotient space means what? V is a vector space and W is a subspace, and all the elements of V by W will take the form W plus V. Okay. Right. Now let's find. See, T of V equal to V they have given, no, W plus V. T of V equal to W plus V. So kernel of T will become, kernel of T means what? The set of all elements of V which are mapped to the 0 element of this space. Look at this space. This is V by W. No, every element will take the form W plus V. So what is the 0 element of this space? W plus 0. Okay, the 0 element here is what? W plus 0. That is simply W. So kernel of T is equal to what? W, because if W is a subspace, no, if that element belongs to W, you will get W, otherwise it will be something different. So kernel of T equal to W. So dimension of kernel of T equal to dimension of W, and hence nullity of T equal to dimension of W, and rank of T equal to, see, already we have a formula, no, that is rank plus nullity equal to dimension of V. From that formula I am writing rank of T equal to dimension of V minus dimension of W. Otherwise, if you want to find the rank directly, how to find? Rank of T is nothing but what? Dimension of T of V, no? What will be the dimension of T of V? Here, for the elements which are in W, it will become simply W. Which are not in W only, you will have what? W plus V. So, rank is nothing but dimension of V minus dimension of W. Okay, right. Then next problem, T from V3 of R to V3 of R defined by T of ABC equal to A00. Now I am going to do this problem in a different way. In all the previous problems, we are not mentioned about the vector space. That is, for any general vector space they have given. But here specifically they have given from V3 of R to V3 of R. So here I am going to find the rank and nullity using the basis of the domain. Okay, or this is the domain, no, that is V3 of R, that is R cross R cross R. So what is the basis for this space? Basis is 1 0 0 0 1 0 0 0 1. Now I am going to find what is range of T. That is range, first I am going to find, from that I am going to find what is the dimension of T of V. Okay, so range of T is nothing but span of T of the basis of the domain. That is, first you write the domain, that is the basis for the domain, and you take the image of all the points, T of 1 0 0, T of 0 1 0, T of 0 0 1. Whatever space this one is spanning, that will become your range of T. Understand? That is, range of T is nothing but the span of this set. Now, T of 1 0 0. What is the definition of T of ABC? A 0 0, isn't it? That is, the first element will be kept as it is. The rest of the elements are 0. So here first element is 1. So 1. Rest of the elements 0. Whatever may be here, it has to be 0 here. And similarly, T of 0 1 0. First element you write as it is, rest of the elements you have to put 0. And similarly t of 0 0 1, first element write as it is, remaining elements you have to put 0. Now look at this, we have to find what is the space spanned by this set, isn't it? See, 0 0 0 we can remove because it can be spanned by the single vector 1 0 0, isn't it? Okay, because, and also you can say it like this is a zero space, no, so it has no dimension. So R of t is spanned by simply 1 0 0. Okay, right? So what is the dimension of this space? Dimension equal to 1. Why it is 1? Because it is spanned only by a single vector. So dimension of t of v equal to 1 implies what? Rank of t equal to 1. Okay, but look at this one. What is the dimension? 3, because we know, no, this is of dimension 3. So rank is equal to 1 means nullity equal to what? 2. Okay, you can also find the nullity first. How will you find the nullity? Nullity is equal to what? Dimension of kernel. So what do you mean by kernel? The elements which are mapped to 0. Look at this definition. Already the second and third coordinates are mapped to 0. Only the first coordinate you have to look at. For what value of the first coordinate this will be mapped to 0? That is what? For all values of 0. Okay, for all values of 0 b comma c, this will be spanned by kernel of t, isn't it? So kernel of t is of dimension 2, that is 0 comma x comma 0 comma y comma 0, another one is 0 comma 0 comma z. Okay, instead of finding the kernel, this will be quite simpler. So you can find the rank and then you can write the nullity. Okay, otherwise you can do in the reverse order also, right? Then next one, let V denote the set of all polynomials of degree less than or equal to n in R of x including the 0 polynomial. Okay, so what is V? Set of all polynomials of degree less than or equal to n over the set of real numbers. T is a mapping from V to V defined by T of f is equal to df by dx. So for this T, for this linear transformation, we are going to find the rank and nullity. So I am going to proceed as in the previous problem because I know what is this vector space now. So I am going to write its basis. So what is the basis of this vector space? 1x, x square, etc. up to x power n. This vector space is of dimension n plus 1 because how many elements are here? N plus 1 elements. So this is of dimension n plus 1. So with this basis I am going to find what is the range of t. So range of t is the span of the image set of this basis. So what is the image set of this basis? Span of t of 1, t of x square, etc. t of x power n. Now let us apply the definition. What is t of f? df by dx, that is differentiation of the polynomial. So differentiation of 1 is 0, differentiation of x is 1, differentiation of x square is 2x, and x cube will be 3x square, etc. x power n is what? N x power n minus 1. So for finding the dimension you have to omit the 0 vector, isn't it? The remaining vectors are all distinct, isn't it? Because one is 1 constant, here it is constant, x term, x square, etc. x power n minus 1. So all are independent. So what is the dimension of the space spanned by this? Only n. That is I am omitting this 0. Wherever you get 0 you have to omit. Remaining vectors count. How many vectors are there? See, these are n minus 1 plus 1 number is there, no? So totally how many vectors are there? N vectors. So dimension of t of v equal to n. Therefore rank of t equal to n. So what is nullity? Nullity is equal to 1 because the domain is of dimension n plus 1, no? So rank is equal to n implies nullity equal to 1. So let me find the nullity directly. Okay, either you can follow this way or this way. Here, see, I am going to find the nullity. For finding the nullity, I have to find what is the kernel. Kernel is equal to, kernel means what? The set of elements of V which are mapped to 0. Look at the definition of T. What is T? Differentiation of the polynomial. When will you get 0? When will you get 0 for polynomial? While differentiating only for constant polynomials. That is, when you differentiate a constant polynomial, you will get 0. Okay, so kernel of t contains the collection of all constant polynomials in R of x. That means just numbers 1, 2, 3 like that numbers. So they are generated by single number 1, isn't it? Because already you know dimension of the real numbers r over r is 1. All the videos that I have posted in linear algebra, I have given the link in the description box. You go through the videos. Okay, so constant polynomials means just they are real numbers. The real numbers, the set of real numbers, no, it forms a vector space of dimension 1. So dimension of kernel of T equal to 1, that is nullity equal to 1. So when the nullity is equal to 1 and this is of dimension n plus 1. So rank will be what? N. Okay, so this is somehow simpler than the previous way. So you can do in any one of the ways. Next one, T from P2 of R to M2 of R. Here slightly I have taken a different notation. This P2 of R is nothing but set of all polynomials of degree less than or equal to 2 over the real numbers. Okay, right. To M2 of R. M2 of R is nothing but the set of all 2 by 2 matrices over the field of real numbers. Okay, so from polynomials of degree 2, we are going to matrices of 2 by 2 size. Okay, how the function is defined? T of f of x is equal to, here it is a polynomial, no, so f of x, but here it is a matrix, no, so matrix of f of 1 minus f of 2, 0, 0, f of 0. This means what? Value of the polynomial at x equal to 1 minus value of the polynomial at x equal to 2. Here value of the polynomial at x is equal to 0. Okay, so what is the basis for this one? This is polynomial of degree 2, no? So 1x x square is the basis. This is of dimension 3. So this is the basis. So range of T is given by span of the image of this basis. So span of T of 1, T of x square. Now let us substitute here. T of 1. T of 1 means what? Here you have to substitute 1. That is f of 1. This is a constant polynomial, no? So whatever value you substitute, what will you get? 1 only. So 1 minus 1. F of 1 minus f of 2. 1 minus 1 because this is a constant polynomial. 1 minus 1. Next one is 0. So 0. Next one here 0. Next one here f of 0. So 1 because this is a constant polynomial. So for all values it will become 1 only. Comma. Next one T of x. So here what is this polynomial? X. So f of 1 is equal to 1. That is this is what? Identity, isn't it? F of 1 is equal to 1 minus f of 2 is equal to 2. Comma 0, comma 0. Here f of 0 is 0. Okay, comma this is square. That is whatever value you have to square it. So f of 1 will be 1 square 1 minus f of 2 will be 2 square 4 and 0 0 here, and here it is f of 0. So if you put 0 it will become 0, right? So what we have, the range of T is equal to span of 0 0 0 1 minus 1 0 0 0 minus 3 0 0 0. Now you have to find dimension of this space. See, these two are linear combination. That is, if you multiply this by 3, you will get this vector. So you can eliminate this. So only these two are linearly independent. That means the dimension of range of T is equal to 2. So rank equal to 2. So obviously nullity will be 1 because dimension of P2 of R is what? 3. So rank 2 means nullity equal to 1. Then one more problem. T is a linear transformation from P2 of R to P3 of R defined by T of f of x equal to 2f dash of x plus integral 0 to x 3f of t dt. Okay, these have the same meaning as in the previous problem. Polynomials of degree less than or equal to 2 over the field of real numbers. Polynomials of degree 3 less than or equal to 3. Okay, over the field of real numbers. So here for this vector space 1x x square is a basis and this is of dimension 3. Now range of T is equal to span of image of this set. So T of 1, T of x square. T of 1, substitute here, f dash of x, when you differentiate 1 it will become 0 plus integral 0 to x 3 into f of t is 1 here. So 1 into dt. So here 2 into f dash of x is 1, that is differentiation of x is 1. So 2 plus integral 0 to x 3 into f of x is equal to x, so 3t dt, comma here 2 into differentiation of x square is 2x. So 2 into 2x plus integral 0 to x 3 into t square dt. So here it will be 3x, here it will be 3x square by 2, here it will be 3x cube by 3. So it will be simply x cube. Okay, look at the three values. They are each and every one is distinct from the other. So all the three together spans. Therefore dimension of T of V equal to 3. So that means what? Rank is equal to 3. If the rank is 3, nullity equal to 0 because this is of dimension 3. So if rank itself is 3, then nullity equal to 0. In the beginning of the video, I have explained about singular and non-singular linear transformation. No? In that one, I have told you if the rank and the dimension are same, rank of T and dimension of the vector space are same, then that linear transformation is said to be non-singular. That is, that linear transformation is said to be 1, 1. Okay, that's all. Thank you.